Okay, that should put me on. Let's see. Hey, I've actually got 5 viewers. So you guys who are in the chat, who's actually in there watching this? Oh, don't want the sound on. Okay, so for those of you who are here, I'm going to get started in just a minute. I just need some way of being able to watch the chat so I can see your guys' questions. And then we'll begin. If I can't, obviously that's fine. I just would like to be able to respond to your stuff in real time. Should be, I think, easier. Okay, no idea what that password is. Okay, should be over there now. chat. Okay, so it looks like you guys can see the chat and things, so I'm going to go ahead and get started. Please let me know if you are in attendance, maybe sound off in the chat who you are. I'm guessing that Noah is the first one I saw who messaged back here. And if anybody else is there, just let me know so I can kind of keep track of who was able to see this and make sure everybody else knows that the video is up. But I think what we're going to do is jump right back into chapter 9.3. We kind of had to rush through the first part of this, and I know that the slides weren't full screened last class. I did figure out how to fix that, so we can go through the entire slideshow today rather than the second half of it, which is good, I think. And we're just going to review all this stuff about population means, which I'm hopeful is going to be helpful. Let me just make sure I'm not muted. No, I'm not muted. Cool. Okay, so we're going to get started with chapter 9.3. Obviously, we're talking tests about a population mean. Yay. And after this section, we should be able to check conditions for carrying out a test about a population mean. We should be able to conduct a one-sample t-test about a population mean. And we should be able to construct a confidence interval to draw a conclusion for a two-sided test about a population mean. Basically all the same stuff we did with proportions, but now we're doing it again with means. And we want to be able to perform significance tests for paired data, which is like in a matched pairs situation or something like that. We'll talk about that later. So you guys might remember that confidence intervals and significance tests for a population proportion P are based on z values from the standard normal distribution. In the case of population means, though, mu, we're now using a t distribution with n-1 degrees of freedom. So the important thing here is that in means we're doing the t distribution, not the z distribution. Except in the rare case when the population standard deviation, sigma, is known. And I think I've mentioned this a couple times in class. That's a really weird case. It probably won't pop up that often. We learned how to construct confidence intervals for a population mean in section 8.3, and now we're going to be doing this testing part. Okay. So in an earlier example, a company claimed that its new AAA batteries lasted longer than its old AAA batteries. Based on years of experience, the company knows that its old AAA batteries last for 30 hours. And they do a simple random sample of the new batteries. They pull 15, which is kind of a little low, as you guys might know. But they see that that simple random sample, the average is 33.9 hours. So that's higher. It's a good sign. With a standard deviation of 9.8 hours. So that's a high standard deviation, so we're going to see if this is convincing evidence that the new batteries actually last longer. So here's what we're doing. Here are our standards, our hypotheses, I suppose. We've got H0, and this is mu equals 30 hours, and we also have HA, and this is that mu is greater than 30 hours. So, of course, mu, if you remember, is the true mean lifetime of the AAA batteries. So we're testing whether or not the new batteries are equal to 30, have a mean equal to 30. So obviously, as always, we have to check our three conditions. Those are random, normal, and independent. The normal condition in this one is a little tricky. The population distribution needs to be normal, or the sample size needs to be bigger than 30. I think Nick told us last time that the central limit theorem is the reason that n needs to be greater than 30. We don't know. In this case, we have a small sample size. So we really need to look at the sample data, which I think is in the textbook somewhere, for any obvious departures from normality, such as skewness and outliers. So I'm actually going to show you that data on the next slide. And here, well, I'll just show you the checks. So we got random, of course this is an SRS. Here's that normal condition. So notice that we've got 3 graphs of the population. We've got a dot plot over on the left. That looks like, doesn't look great, but it's not super skewed. We have a histogram, or no, sorry, box plot in the middle. That, again, doesn't look great. That middle is kind of off, but it's fine. It's mostly not skewed. And then we look at the normal probability plot, and that's pretty close to linear, so I think we're okay. Again, this is kind of what you're looking for in the data, like stuff that maybe isn't perfectly normal, but is at least mostly symmetric and not super skewed with no like huge outliers. Finally, we got to check for independence. We are pulling these batteries without replacement, at least that's what we assume. And so we need to check the 10% condition. There have to be at least 150 new AAA batteries. That seems reasonable for a company launching a new product line, so we're going to believe it. Okay, so carrying out a significance test. What we need to do, as we did when we did proportions, is find a test statistic and use that test statistic to find a p-value. Now, in the case of the proportion, we used a test statistic that was a z-score. In this case, we are going to be finding a t-score, or a t-value, I suppose, but the process is very similar. Again, we're doing statistic minus parameter divided by the standard deviation of the statistic. Now let's look at what that actually looks like in the formula. This is the standard deviation for the sample mean. Now, because the population standard deviation sigma is usually unknown, we use that S sub x in its place. So the resulting test statistic t looks like this. We do x bar minus mu, that's mu null, divided by Sx, which is the sample standard deviation, divided by root n. And again, the reason we use S sub x rather than sigma is we don't know sigma, so we kind of approximate with the standard deviation of the sample. When the normal condition is met, meaning what we proved on the last slide, this statistic is going to have a t-distribution with n minus 1 degrees of freedom. I'm sure you guys remember that. Okay, so now let's get into the actual calculation of this test statistic and, lost my train of thought, the p-value. So, again, the test statistic is going to be statistic minus parameter divided by the standard deviation of the statistic. So that's going to be x bar, or 33.9, minus mu null, or 30, divided by S sub x, which is 9.8. That, in turn, divided by root 15. Remember that the sample size is 15. Okay, so that gives us a t-value of 1.54, which is awesome. Now we're going to have to go to our TCDF, and we're going to run a TCDF from 1.54 to, you guessed it, infinity. So this is a t-distribution, again, with degrees of freedom equal to 14, and we're looking for the probability that that t-value would come out 1.54 or higher. Now they're going to show you how to do this with the table. I strongly recommend you don't do this with the table. Just use your Inspire or your 84. Run a TCDF from 1.54 to infinity, or as close as you can get with the 84, and that should give you a p-value. Remember that the degrees of freedom are going to be 14 because the sample size is 15. Okay? So and what we see is that, I wish they gave you an actual p-value, but I'm sure you guys can calculate it. I know it's a little higher than 0.05. So because the p-value is not less than 0.05, we cannot conclude that we have sufficient evidence to say that the company's new AAA batteries last longer than 30 hours. Responding to a quick message. So again, we remember that phrasing. We lack sufficient evidence to conclude that the company's new AAA batteries last longer than 30 hours. Have we proven that they don't last longer than 30 hours? No, we have not. Have we proven that they last exactly 30 hours or less than 30 hours? No, we have not. So remember, we haven't proven anything. We've just failed to disprove something. Obviously, there's a difference between failing to reject and accepting a hypothesis. Let's move on. Using table B wisely, I would say probably the best way to use table B wisely is not at all. Again, your TCDF will do this a lot faster and a lot better. You notice that in table B, I'm not sure we've even looked at table B that much, but they skip a lot of the degrees of freedom. So we don't really want that. It's really going to give you an approximation, whereas using your calculator is going to be a lot more accurate. It also doesn't work for negative values, so let's just skip that. Okay. What we're doing here is, suppose we're performing a test of null hypothesis mu equals 5 versus the alternate hypothesis mu does not equal 5 based on a sample size of n equals 37 and obtains t equals negative 3.17. What I'm going to show you here is how you could use the table to find a probability. However, you can do this in your calculator a lot faster, so I would recommend you do it that way. Due to the symmetric shape of the density curve, the probability that t is less than or equal to negative 3.17 is going to equal the probability that t is greater than or equal to 3.17. So because table B only gives positive t values, we got to find the one for t equals 3.17. So we look over here at the table. Remember that our sample size here is 37. Since we do not have, since we do not have quite 40, we're going to use 30, which is less than. You always want to use the degrees of freedom less than the one you have available. And this is going to be somewhere between these two, so the probability is going to be somewhere between 0.0025 and 0.001. Is that going to be significant enough in almost all cases? Sure it is. So this one would give us enough evidence to reject H0. Okay. Again, I'm going to strongly recommend that you shy away from using table B. Please do write these probability statements. These are very helpful for the AP graders to read. However, I would get used to using your calculator and the norm CDF and TCDF functions rather than going to the tables. Okay, so if the conditions are met, we can test a claim about a population mean mu using a one-sample t-test. So this is just what we were doing earlier. We find our test statistic. That's t equals x bar minus mu null over sx divided by root n. By the way, I did not mention this earlier, but I am recording this video, so I'm just gonna post it. I'm gonna post it again after it's done. So if I'm moving too fast through any of this, this will be posted. You can go back to it and like pause the video here and be able to copy this down in your notes or something. So I'm gonna keep moving, but just know that it's gonna be uploaded later. You can find the p-value again by calculating the probability of getting a t statistic this large or larger in the direction specified by the alternative hypothesis HA in a t distribution with df n minus 1. Remember that we have three possibilities for our HA. Either mu is greater than mu 0, in which case we're looking only greater than our t statistic, or HA is that mu is less than mu 0, in which case we're looking only less than our test statistic. But then we have this other HA where mu is just different from mu 0, in which case we need to double that area. I am getting a request in the Twitch chat to play Mine Diamonds. I'm not going to do that. Sorry to disappoint, guys. Who is Trump Duterte 2020? I don't even know who Duterte is. Anyway, moving on. In the most readable font ever, you should use this test only when the population distribution is normal, or the sample is large, and the population is at least 10 times as large as the sample. So that's just a reminder, you do have to meet your conditions. And of course you do want the sample to be random, right? You don't want a non-random sample because that can lead to bias. Okay, so here's another example. The level of dissolved oxygen in a stream or river is an important indicator of the water's ability to support aquatic life. A researcher measures the DO level at 15 randomly chosen locations along a stream. Here are the results in milligrams per liter. So what we're seeing is a lot of data here, obviously, and we're noticing that a dissolved oxygen level below 5 milligrams per liter, notice we're saying below, that means we're doing a one-sided test, puts aquatic life at risk. And we got all this data. Now, Ms. Jenkins has been great about the advice. When you see data, put it in your calculator. I would recommend the same thing. The second you see this big list, you probably want to start entering it into your into your calculator, being very careful to record each number correctly. Otherwise, you'll have some big problems later. But that's going to make your life a lot easier. So I'm going to walk through this one with the state, plan, do, conclude method. And for the state step, all you really need to say is what the alpha level is, what the H0 is, and what the HA is. And you do want to define your mu. So in this case, mu is the actual mean DO level in this stream. Notice that these are all just different numbers, and we're testing whether or not it's equal to 5, and notice our HA is that it's less than 5. We don't really care if it's bigger than 5. All we know is that this DO level below 5 would put aquatic life at risk. For the plan step, we need to check our conditions. So if conditions are met, we're going to do a one sample t-test for mu. Notice, we only have one sample here. It is 15 measurements, but that's one sample. It is random. We got the DO level at 15 randomly chosen locations. If we looked at the data, we can see that it's normal. You see a roughly symmetrical histogram, you see a roughly symmetrical box plot, and you see a roughly linear normal probability plot. So I think we're good to use T procedures. Remember, if n was greater than 30, we'd be good to just go ahead and assume that because of the central limit theorem, we wouldn't have to check the distribution. There's one more condition we need to check, and that's independence. We can see that there's an infinite number of possible locations along the stream, so it isn't really necessary to go through the math and check the 10% condition, although I also think writing out there will be more than 150 possible positions on this stream is going to be just fine. We do kind of have to assume that each individual measurement is independent, but that seems reasonable. There's no reason to me to believe that one point on a stream would influence another point on a stream, besides the whole stream kind of influencing both of them. Okay, for the do step, now we have to actually calculate our t-statistic and our p-value. So the sample mean and standard deviation, this came from putting this into my calculator, are x bar equals 4.771 and s sub x equals 0.9396. So I'm going to go through and actually calculate the test statistic. So we're going to do x bar minus mu. That's going to be 4.771 minus 5. And we're going to divide that whole thing by s sub x over root n, which is going to be 0.9396. Again, that's something that the calculator gave me based on the one variable statistics. And we're going to divide that s sub x, by root 15. Okay, that's going to give us a t statistic of negative 0.94. For the p-value, that's going to be the area to the left. Notice only to the left because we're looking for the probability that mu is less than 5. The area to the left of t equals negative 0.94 under the t distribution curve with degrees of freedom 14. Again, remember we're doing sample size minus 1. So again, for some reason, the slides are going to point you towards table B, and you got to give us some credit here. These are old slides. I'm not even sure the Inspire was out yet when these got rolled out. So they're going between, well, if you were doing this on your calculator, you'd want to do the TCDF from negative 0.94 to negative infinity with degrees of freedom 14. The way they're going to do it is look along the degrees of freedom column, and you find the closest two values. So it's between 0.868 and 1.076 because it's 0.94. Remember that the t thing only does positive. So the p-value is going to be somewhere between 0.15 and 0.2. Remember, if the lower bound, which is in this case 0.15, is greater than 0.05, we're going to fail to reject. And also recall, well, one thing I want to point out, they did not give you a specific alpha level in this problem. When they don't give you an alpha level, you should use 0.05. Unless they specifically give you an alpha level, you should probably default actually to 0.05 because that'll be the kind of standard. So again, we don't have enough evidence to conclude that the mean DO level in the stream is less than 5 milligrams per liter. Be very careful here. Once again, do not say we can conclude that the mean DO level is 5 milligrams per liter. We are not going to accept that it's not less than 5 milligrams per liter. We're just failing to reject the H0 that it is 5 milligrams per liter. Now, we did not reject H0. It is entirely possible that we could have made a type 2 error. That would be failing to reject H0 when H0 is false. Let's think about that in context. If we had made a type 2 error, then the mean DO level, mu, in the stream is actually less than 5, but we didn't detect that with our significance test. One reason I'm going to say that a type 2 error in this case is slightly a little likely is we probably don't have a very high power to this test. And the reason I'm saying that is because our sample size is only 15. Generally, low sample size is not great for being able to show significance. So that's my one kind of thought here. I'm going to pause because we're about to start the second half of this presentation, which actually is great because we're right on track to be here for no more than an hour. So I'm going to pause on this slide, and if you guys, for about a minute, if you guys have any questions, maybe put those in the chat and I'll do my best to answer them quickly, and then we can move on to our next section, which is going to be 9.3b. Okay, I think let's get back to it because it doesn't look like you guys have any questions besides whoever said very cool Kanye. So indeed, very cool Kanye, very cool. Let's move on in. We're now going to talk about two-sided tests and confidence intervals, and if you look sideways on the screen for a moment, you'll see that we're also going to try to cover paired t-tests for match pairs design studies. Okay. So let's talk two-sided tests. At the Hawaii Pineapple Company, which I'm told is a real thing, managers are interested in the sizes of the pineapples grown in the company's fields. Last year, the mean weight of the pineapples harvested from one large field was 31 ounces. A new irrigation system was installed in this field after the growing season, and naturally we want to see if it's effective. I'm going to pause for 1 second because Scott actually, or it looks like Scott just put a question in the chat about the power of the last test. Scott, here's what I'll say about power. We don't really teach calculations of power in this course, but generally if the sample size is bigger, we have a higher power. I'm going to put that in the chat as well. So give me 1 second of pause here. Okay, got back to that, so I'm going to keep moving. So, again, basic idea of this problem. We did some stuff, like we grew some pineapples last year. They were an average weight of 31 ounces. We put in a new irrigation system. We want to see if that actually made the pineapples bigger. So to find this out, we select and we weigh a random sample of 50 pineapples from this year's crop. That's, just off the bat, that's really good because we took 50 pineapples, which means we're going to have that n greater than or equal to 30 right off the bat. So the mini-tab output, and we've seen mini-tab output before, the mini-tab output below summarizes the data. So using this mini-tab output, determine whether there are any outliers. So we are looking at the descriptive statistics here. I see the standard deviation of the sample was 2.394. I see the mean was 31.9. So that looks like maybe it's a little bigger than last year. We're going to see if that's significant or not in a moment. And you can also glance over the 5-number summary if you want, but that we're not really interested in that right now. But we do see the... Oh, okay. Yeah, this is a good point, actually. We should check for outliers. So we can calculate the IQR, which is going to be 4.125. If any data value is greater than Q3 plus 1.5 IQR or less than Q1 minus 1.5 IQR, that's going to be an outlier. So we run through that math and we see that that range goes from like 23 to 40. All our values are between 26 and 35, so we're actually good here. We don't have any outliers, which is good. Okay, so we want to test the hypotheses. The null hypothesis is that mu is 31, basically same as last year. Or the alternate hypothesis is that mu is not 31. Now notice, in the original problem, let's jump back just for a second. We wanted to see if the change would affect, and I'll highlight or mouse under this, we want to see if the change will affect the mean weight of future pineapples grown in this field. But maybe I can, yeah, let me laser point this. Will affect the mean weight of future pineapples grown in the field, but we don't necessarily have a direction there. So what we're going to do is use a two-sided test. That is to say that mu is not equal to 31, but not necessarily give a direction to it, okay? So since, again, no significance level is given, we're going to use alpha of 0.05. This doesn't advance the slide anymore, I guess. So if conditions are met, we're going to do a one-sample t-test from mu. Now remember, again, we're using that state plan, and we're going to do conclude after this. State is where you put down your hypotheses and your significance level. plan is where you tell us what kind of test we're doing. So in this case, one sample t-test from you. We're going to check our conditions. So random, yep, they told us this was random. Normal, we have n equals 50, which is bigger than 30, so we're good to use t-procedures. And of course we have independent. There probably are going to be at least 500 pineapples in a large field. Remember that this is a pineapple company, so we're going to assume that they probably grow a lot of pineapples. Okay, for the do step, now we get into actual calculations. So the sample mean and the standard deviation, these are in the mini tab output, remember. So x bar is going to be 31.935. S sub x is going to be 2.394. There we go. So again, that test statistic formula, T equals x bar minus mu null divided by S sub x divided by root n. And I love that somebody just put in the chat, state, plan, do, conclude, because that is the model we're following. So let's plug some values in. We do 31.935 minus 31 divided by 2.394, which is the S sub x, divided by root 50. We punch that into the calculator because I don't think anybody in here wants to do that by hand, and we get 2.762. Now, right off the top of my head, I'm seeing a t value that's greater than 2. I'm guessing that's going to be significant, but we're going to have to see. So, the p-value for this two-sided test is going to be the area under the t-distribution curve with 49 degrees of freedom, 50 minus 1. They're going to use table B, which is a little annoying, but so you have it. They don't have an entry for df equals 49. So we're going to use the more conservative df equals 40. Remember, always use, if you are using table B, you want to use the degrees of freedom that are less than the ones we actually have. The upper tail probability, I think they'll highlight this, yeah. That 2.76 is going to be somewhere between these two probabilities. Remember, we do have to double these because it's a two-sided test. So the desired p-value is going to be between 0.01 and 0.005. Those are some very low p-values. So it's definitely going to be less than our alpha equals 0.05 significance level. That means we've got enough evidence, or you could say sufficient evidence, to reject H0 and conclude that the mean weight of the pineapples in this year's crop is not 31 ounces. Please notice a couple things. We did not ascribe a direction to this conclusion, right? All we're concluding is that the mean weight of the pineapples in this year's crop is different from 31 ounces. Not less, not more, just different. I also like, this is a great part of this response, that they actually said weight of the pineapples in this year's crop. That is putting the answer in context. Remember, a couple of you are still struggling to put the context of the problem back in your conclusion step, and that is exactly what you're supposed to do with this step. I know this looks like kind of a meaty paragraph, but it really, if you look at it closely, it's one sentence connecting the p-value to a reject or fail to reject, and then putting that decision in some context here. So it's kind of a three-part answer, but it doesn't have to be incredibly lengthy. Okay. What we do now is we go in and we actually find the confidence interval that matches that test. So you'll notice if we do the 95% confidence interval here, this is actually, I think, if we run the mini-tab output significance test. So there again, they came up with a t value of 2.76, and if you I'm going to pause for 1 second because someone asked a great question in class or in the chat, and I'm going to jump back. So the question asked was, during the conclude step in a problem, is this the typical wording for the question? And I would say, yeah, this is pretty good wording for this question. The only thing I would do differently in this whole problem is when it comes to finding the p-value, I would not go to table B. I would go right to the calculator, do a TCDF, show that that's the probability of t being greater than 2.76 or less than 2.76. And on the next slide, we're actually going to get to see the p-value. I would say that p-value is less than our alpha, so we have sufficient evidence to reject H0 and conclude that the mean weight of the pineapples in this year's crop is not 31 ounces. I love the back half of their sentence. This whole, so we have enough evidence to reject H0, blah, blah, blah. Okay, looks like you got it, so I'm going to move on. Remember, just use the calculator to find those p-values. And again, we do see that p-value over here with a t of 2.76 and degrees of freedom of 49. We do come up with a p-value of 0.008, which of course is going to be significant at the alpha level 0.05. Now, the 95% confidence interval, remember, this gives us a little more information. We've got 31.255 as our bottom lower limit, and we got 32.616 as our upper limit of this confidence interval. Notice, it does not include 31, which of course lines up with our significance test, because our significance test says it's not going to be 31. However, the confidence interval, if you remember, gives us a little more information. It says that the mean weight of the pineapples is going to be between 31.255 and 32.616. So we're 95% confident that this interval captures the true mean weight mu of this year's pineapple crop. All right, that is a heck of a color. So as with proportions, there's a link between a two-sided test at significance level alpha and a 100 times 1 minus alpha confidence level for a population mean mu. That's a mathy sentence, but all it means is that the percent alpha level, if you translated that alpha level to a percent and subtracted that from 100%, you'd wind up with the confidence level of the confidence interval that kind of lined up with it. So in other words, if your alpha level is 0.05, which is 5%, your confidence level is going to be 95%, and that's going to kind of line up there. So for the pineapples, the two-sided test at alpha equals 0.05 rejects H0, and the corresponding 95% confidence interval does not include 31 as a plausible value of the parameter. So basically, the test and the interval agree. They come to the same conclusion about H0. But the confidence interval does involve, well, it says much more information. I would say it provides some more information, a set of plausible values for the population mean. Notice, if we just know that this thing is not 31, that's not incredibly helpful, but the confidence interval says it's probably like a little bit more, which is actually really good. It's very good feedback to have. Gentlemen, whoever posted the fitness gram pacer test information in the chat, that's a heck of a paragraph. Appreciate that. So the connection between two-sided tests and confidence intervals is even stronger for means than it was for proportions. That's because both inference methods for means use the standard error of the sample mean in the calculations. All I mean by that is this. You notice that S sub x divided by n is used as the standard error over here. And we notice that S sub x divided by root n is used as the standard error over here. I'm going to mostly skip through this slide. I think you guys are kind of grasping the idea here. Basically, if you are going to reject H0, your confidence interval is not going to include the mu0. If you fail to reject the null hypothesis, the confidence interval probably will include mu0. If there's any questions on that, please put them in the chat, and I'll answer them as soon as I can. But that's the basic idea here. If you reject, then the confidence interval probably doesn't include it. If you fail to reject, then the confidence interval probably does include it. Okay. Last thing we're going to talk about for the day is paired data. So most of the time when you're doing a good study, you want to have some kind of comparison step. So one sample inference is often a lot less common than comparative inference, and study designs that involve making two observations on the same individual or one observation on each of two similar individuals result in what we call paired data. So when we have paired data, what we're really going to be analyzing is the differences in each pair, and we call these paired T procedures. There's a bunch on this slide. You can go back and watch it later if you want to write every word down, but for now I don't think that's that valuable, and I want to get into a practice problem so you can see how this works. Okay, big paragraph. I'm going to break this down for you guys. So we have an experiment where we are looking at the effects of caffeine withdrawal. Remember way back in chapter 4 or 5, when we talk about an experiment, it means we're actually applying conditions to subjects. We're not just watching them do their normal thing. So we recruit 11 volunteers who were diagnosed as being caffeine dependent to serve as subjects. So everybody in this study presumably is caffeine dependent, and those are all our subjects. We bar all subjects from coffee, colas, and other substances with caffeine for the duration of the experiment. So they're essentially Mormons. Cool. During 1 2-day period, subjects take capsules containing their normal caffeine intake. So there's a 2-day period where subjects are taking capsules with their kind of standard caffeine intake. During another 2-day period, they're taking placebo capsules. The order in which subjects took caffeine and the placebo is randomized. So by that, I'm assuming they mean some subjects are taking the caffeine first, and some subjects are taking the placebo first, with the other one being the second thing they take. That's always good. The more randomization, obviously, you can include in the study, the better. You wouldn't want to do, for example, give everybody the placebo first, and then everybody the caffeine second. That might be a lurking variable issue there. At the end of each 2-day period, a test for depression was given to all 11 subjects. Researchers wanted to know whether being deprived of caffeine would lead to, wait for it, an increase in depression. So I'm sure some of you can guess. Maybe put answers in the chat. What will the direction of our alternative hypothesis be? Is it going to be a less than, not equal to, or greater than? Gonna wait just a little longer, see if I can get a response or two in the chat. I might not, that's okay. Okay, I don't see anybody getting back to it. If you did get a guess in, I'm on a bit of a delay, so I might not have seen it yet, but basically this, because we're looking at an increase, we are going to use an alternate hypothesis that has a greater than in it. So we'll get to what that looks like in a minute. Here are our data points. So notice in the first column we got the depression score with caffeine, and then we've got the depression score with the placebo, and what we're looking for in the difference is how much greater the placebo was than the caffeine. And one thing I want to notice, we have positive values for everything except the 11th data point. So that means that there was more depression in the placebo condition than there was in the caffeine condition for all but one subject, which is kind of promising so far because that's exactly the direction that we predicted. All right, so we're going to go through that state, plan, do, conclude method again. By the way, you do not have to write all this much for the state step. What I would do is say H0 equals mu of the difference, and that the H0 is going to be that that's 0, so there is no difference, and the HA is going to be that it's greater than 0, meaning the difference is positive, meaning an increase in depression. And you do want to define your mu D. That's going to be the true mean difference, placebo minus caffeine in depression score. Some things I want you to be really careful of here. Make sure you define this as a true mean difference and tell the grader what you're doing. So like placebo minus caffeine, be sure to list that off in depression score and make sure they just really understand what your mu D is from the get-go. There's no significance level given. Remember, if there's no significance level given, we are going to use alpha equals 0.05. Great transition. So now our plan step. We do need to hit those conditions again. If the conditions are met, we're going to do what's called a paired t-test for mu D. So as far as random goes, we did randomly assign the treatment order, and I'm assuming that, yeah, that was randomly assigned to the 11 subjects. Now, no idea how they split the 11 subjects down the middle, or I'm not sure what method they used. I'm going to hope that it was something good and truly random, but we'll trust them on that. Next up, we don't know whether the actual distribution of difference in depression scores is normal. And unfortunately, in this case, the sample size is small. We only had 11 subjects, which makes sense because this seems like kind of a long and maybe expensive experiment. We do need to look at the data to see if it's safe to use T procedures. We see sort of a normal-ish histogram. We see sort of a symmetrical box plot. We see sort of a linear normal probability plot. We're going to kind of hope that this works, basically. At this point, looking at this data, I would recommend you put down, like, this might be a little bit skew, but I think it's normal enough that we can go ahead with our test. And for independence, we aren't sampling, so we don't have to check the 10% condition. Remember that if this is an experiment, we actually don't need to sample randomly. We will assume that the changes in depression scores for individual subjects are going to be independent. That seems reasonable if the experiment is conducted properly. We're not going to assume that one subject's depression score is going to affect another subject's depression score. Obviously, we don't know exactly how interactive this study is, but that seems like a reasonable assumption here. Now for our do step, kind of the most fun. We have a mean difference equals 7.364. Remember, as always, I would hope that you're putting data into your calculator and letting the calculator handle this math for you. The standard deviation of the difference is going to be about 6.9. We go through and we calculate a test statistic T. I don't think I need to go through all that this time. And hey, look, this time they actually used the calculator. So according to technology, yay, that means your Inspire or your TI-84, the area to the right of T equals 3.53, which is the T-score they came up with on the T distribution curve with DF equals 10, is going to be 0.0027. So I hope you all are at the point where you can recognize that's going to be significant. So here's a conclude paragraph that I really like. With a p-value of 0.0027, which is much less than our chosen alpha equals 0.05, we have convincing, or you could say sufficient, evidence to reject H0, which is that mu D equals 0. We can therefore conclude that depriving these caffeine-dependent subjects of caffeine caused an average increase in depression scores. This is a paragraph I really like because the first part kind of shows what the p-value leads us to, and then the second sentence puts that in context. So someone was asking in the chat on the last one, is this what a conclude statement should look like? I think with the last one, I didn't love it because it wasn't based on the calculator numbers, but this one is. It gives an exact p-value, and it says that p-value is less than alpha. That means we should reject H0, so that leads us to conclude this. That's the phrasing I like to see and the formatting I like to see in this conclude step. Okay. Oh yeah, and they're showing here just how you would actually do that. You can actually in your calculator put in a stat calculation, which is just going to find the difference between the two columns. I can show you guys how to do this in school if you're interested. We can go over this. This is really kind of a mess of a slide, but you can actually do even a t-test in your calculator, and that'll give you exactly what we just talked about with the t equals 3.53 and p equals 0.00727. I'm going to move on. So using test wisely. I got some bullet points. Just keep in mind when we want to use significance tests and when we need to be a little careful about them. I do want to pause for a moment on this slide because they give a lot of great examples of when significant tests are used. New drugs need significant evidence of effectiveness and safety. Courts often ask about statistical significance in hearing discrimination cases. So sort of like what's the, how unusual would it be to have done X, Y, or Z action, maybe in a job interview process, etc. Marketers want to know whether a new ad campaign significantly outperforms the old one. And medical researchers want to know whether a new therapy performs significantly better than the old therapy. And whether it's just as, you want to look for safety concerns too. In all these uses, statistical significance is valued because it points to an effect that is unlikely to occur simply by chance. And of course, you can modify your alpha level to determine what that chance of something happening randomly actually is. So let's look at some points to keep in mind when interpreting significance test. So first of all, when a null hypothesis, no effect or no difference can be rejected at the usual levels, there's good evidence of a difference, but that difference might be kind of small. So basically, the bigger your sample, even tiny deviations from the null hypothesis can come out significant. Now, all that means is that if you have a big enough sample, you might notice a significant difference, but your effect size, meaning the actual difference between the two things, might be really small. So to give an example of this, if that pineapple company we'd been looking at earlier put in their new irrigation system and they took a sample of like thousands of pineapples, even if the difference were as small as like 1/100th of an ounce, they might get a significant difference. Now, that's still a significant difference, but 1/100th of an ounce is probably not enough for them to continue investing in what's possibly a very expensive irrigation system. So you do want to keep that in mind. If you have a huge sample size, you might get a significant result even with a very small effect size. Some more points here. First of all, don't ignore lack of significance. There is a tendency to kind of infer that there is no difference whenever a p-value fails to attain the usual 5% standard. That's not really true. That is kind of accepting the null hypothesis when we really should be failing to reject the null hypothesis. There are some areas of research where small differences that are detectable only with really big sample sizes can be of great practical significance. When planning a study, you need to kind of check that the test you plan to use has a high power or probability of detecting a difference of the size you hope to find. Statistical significance is not valid for all sets of data. The idea here is basically if you have a badly designed survey, if you have a badly designed experiment, those are going to produce invalid results. Just because you do your test correctly doesn't mean that the data used in that test was actually good data. Properly produced data is kind of the most important part of this whole testing process, and if your data is shoddy, then the whole thing is kind of a moot point. And finally, you want to be aware of multiple analyses. Statistical significance should mean that you found a difference that you were looking for, and the reasoning behind statistical significance works really well if you decide what differences you're looking for, design a study to search for that, and use a significance test to weigh the evidence you get. One thing that it often does get used for, and it's not really meant this way, is to test a whole bunch of things at once, see what's significant, and kind of run away with that as your paper's title. That is a little iffy practice. It does pop up a lot in the social sciences. If you have more questions about that, I'd be glad to talk about it in class. Okay, so I think I'm going to wrap up there. This is the summary slide. Basically, the idea is if we often are going to be doing one sample T statistics in this chapter. We are sometimes going to be doing paired t-tests in this chapter, but that actually brings us to the end of significance tests chapter, which is awesome. For you guys who came into the stream today, thank you very much for setting aside some time on your snow day to do some stats. I appreciate that a lot. To whoever just posted in this stream chat, this is not a Dota stream, but is it popping up as a Dota stream? That's really funny if it is. I hope you got some information from today. I am going to post this video on my website. I'll give you guys a link once that's up. And if anybody has any questions, please feel free to email in. The Slack chat is still up for those who are in it. But email is great. And if you have any questions on the video, I can also follow up in class tomorrow. We are going to try to do a review day in class tomorrow. Because you guys don't have the review test, this is going to be a little more challenging, but I am going to pass it out tomorrow in class, and we'll try to work through, at the very least, the free response, or not the free response, but the multiple choice. And hopefully, assuming there's no more schedule interruptions, hopefully we'll have time to also do 1 or 2 free response problems, so you guys have a sense for what to do on the test. The test will be, as far as I know, next Monday. And I just want to warn you guys, I am not in school this Friday. I am going to a math conference. But if you do want to see Miss Jenkins for extra help, I believe she will be available Friday's study hall. So please feel free to check in with her if you need any assistance there. I'm going to now shut down the stream. I'm not going to play any of your song requests because you're suggesting terrible song requests. But I will see you guys in school tomorrow. And until then, enjoy your snow day.